Hello everyone, my name is Milan Lopua-Zwakenberg and my presentation is called The Privacy Funnel from the Viewpoint of Local Differential Privacy. Before we start with that, a little bit about myself. I'm a postdoc in the security group at TU Eindhoven. Here's a picture of my face if you can't see it in the top right corner of your screen. My research interests are data sanitization and privacy and utility metrics in data sanitization. Specifically, I like to research the mathematical and information theoretical properties of such metrics. And one of these metrics that plays an important role is differential privacy because it pops up everywhere because a lot of people are using it. So now back to the talk, which was privacy funnel from the viewpoint of local differential privacy. Let me start by explaining what the privacy funnel is. So we have a database X, and it consists of n rows x1 up to xn, each representing the data from one user. And we want to publish this database. However, every entry is correlated to some secret information, S1 up to Sn. And we don't want this secret information to leak because it's sensitive data. So what we're going to do is we're going to output a sanitized database Y that does not leak information about S, or at least does not leak too much information about S. And we're going to do this by applying a probabilistic privacy protocol Q on every row individually. So we apply Q to X1 and it becomes Y1, etc. And the reason that we do this on every row individually is because it then makes it easier to find the optimal queue. So you only have to optimize on a local level and not over the whole database. And that will turn out to be very nice. So some assumptions before we begin. We assume that both the SI and the XI are discrete random variables. And we assume that every row is drawn from the same joint probability distribution of S and X, and we assume that the owner of the database has access to this probability distribution. That makes sense because, well, he has the whole database, so that does give him some clue about what the distribution is. So given this setting, we want to create a sanitized database. So here's the picture for one of the rows. And we want Y to contain a lot of information about X and as little information about S as possible. One way to measure this is to look at mutual information, both as a utility metric and as an information leakage metric. So this is the typical privacy funnel setting where we want to maximize the mutual information between X and Y while keeping the mutual information between S and Y lower than a certain threshold, which I have written L here. There are two problems with this approach. First, if you take mutual information as a leakage metric, then what you get is an average leakage. So it tells you that the average row in the database will only leak a certain amount of data about S. But then there might be rows that have more leakage than that, and there might be users that will be more compromised than your threshold allows. That is something that we do not want. Ideally, we want to give some privacy guarantee that holds for every user in the database, not just the average user. Another problem is if you want to solve this problem, where you want to maximize mutual information between X and Y, while keeping mutual information between S and Y low, there is no good method to do this. There are some methods, but they will only give you a local optimum, and you might not even find the optimal queue. That is something that we would like. So today we're going to solve both of these problems, but we're going to start with the leakage metric, where here we have mutual information between S and Y, but we would like something that is a bit more worst case. Well, one way to do this is to take local differential privacy as a privacy metric. It's something that is used by a lot of people because it has very strong privacy guarantees and it's easy to calculate. Its precise definition is as follows. So we take epsilon bigger than 0, which is our privacy level, And then we say that Q satisfies epsilon local differential privacy with respect to S if for every two S and S prime that you take and every possible output Y, the probability of getting output Y given secret value S should be about the same as the probability of getting output Y given secret value S prime. To be precise, the difference between these two as a fraction should not be more than e to the power epsilon. And you can see that this gives privacy, because then that means that if you see a Y in the eventual sanitized data set, then the probability of getting that Y starting from S is about the same as getting that Y starting from S prime. So if you see a Y, you don't know if the real data was S or if it was S prime. So this is a definition of privacy. It's used by a lot of people. And we're also going to look at it today, but we're also going to look at a variant of this, which turns out to be slightly more useful in our situation. It's called local information privacy, and it's defined as follows. So here we look at an output Y, and we consider an input S. And what we want is that the probability of getting the output Y should be about the same as the probability of getting output Y if you know that the secret is S. So that means that knowing the secret does not change too much about your probability distribution of the output. So to be precise, we want the fraction to be between e to the power epsilon and e to the power minus epsilon. And in both these cases, how much privacy you actually get depends on the value of epsilon. For both of them, if you take epsilon is 0, that means that Y and S are independent, which is certainly a very strong privacy requirement, but sometimes it may be too strong. And the bigger you take epsilon, the more leakage you allow. There are no hard and fast rules about what makes a good epsilon and what doesn't, but people generally agree that if you take epsilon approximately equal to 1, then you get very decent privacy. Some facts about these metrics. So I have summarized them here to your right for your convenience. Well, both of them are worst case metrics. So they say that no matter what the input is and no matter what the secret value is, you always have certain privacy guarantees. And that is very nice, because that means that we protect the data from all of our users. We also have that epsilon LDP is stricter than epsilon LIP. So if you satisfy LDP, you certainly satisfy LIP. And if you satisfy either of them, then you also have a bound on mutual information. In fact, the mutual information then cannot be more than epsilon. So if you find a protocol that satisfies epsilon LDP or epsilon LIP, then it's certainly a protocol that's appropriate for the privacy funnel setting as is classically defined. So that's nice. Also, both of them depend on the probability distribution of S and X. So in that sense, it's a good thing that we assume that it's known to begin with. This is a bit different from what people usually do in local differential privacy, where it doesn't depend on the input distribution, but that is when you want your output to have differential privacy with respect to X instead of to S. But in our situation, it does depend on the joint distribution of S and X. Now, what does local information privacy mean? Well, if you look at the fraction P of Y given S divided by P of Y, you can calculate that this is the same as the probability of S given Y divided by the probability of S. So that means that if you don't know any data, then you know that the probability of S, then you know that the probability of a secret is just the probability of S. And then it tells you that once you have seen the sanitized data set, then your belief about what the secret value is should not change too much, at most by a factor of e to the power epsilon. So that is nice. So it has a clear meaning about what kind of privacy this gives you. And the same goes for LDP in a certain sense. So it gives the same guarantee that you have a bound between the prior and the posterior, but it gives it even when the probability distribution on S is unknown. Which is nice to have this additional guarantee, but it's not really relevant for the situation we're in because we assumed already that the aggregator has access to the joint distribution of S and X, and in particular to the distribution of S. So in that case, we would rather like to use LIP than LDP because LDP might give stronger privacy, but it is stronger in the sense that it's not relevant. And because it is stricter, it means that you will sacrifice utility for it. And we'd rather don't want to sacrifice utility, so we can conclude that we would rather take local information privacy as a privacy metric. And in fact, we will later see that there's another reason why we want LIP rather than LDP, but we'll get to that later. So given that we have this privacy metric or these privacy metrics, then we can formulate the following problem. So given epsilon, we want to find a Q that maximizes the mutual information between X and Y while still satisfying either epsilon LDP or epsilon LIP, depending on what we want precisely. Now, in the rest of this talk, I'm going to show you two things. First of all, we can solve this problem. We can find the optimal Q. We can find an algorithm to do that. The second thing is we can do this both for local differential privacy and for local information privacy, but it will be easier for local information privacy in a computational sense. So finding the optimal LIP protocol will be faster than finding the optimal LDP protocol. And that is another advantage that LIP has over LDP. But first, let us look at LDP. So we let A be the size of the input space, of the space of possible X, and we let B be the output space. B is something you can choose when you are designing your Q. But if we fix B, then we can consider Q to be given by the matrix G, which is just the probabilities of a given output given a certain input. So if you know G, you know what Q is. And furthermore, there's a theorem, which I'm not going to explain now, that says that the optimal Q, you will get it when B is equal to A. So that means that you don't have to consider all B in your search, you just have to consider one of them. And since Q is given by G, you're actually just looking at matrices with certain properties. So the set of all epsilon LDP protocols is a subset of the real numbers to the power B times A. So it's a subset of that. And we can describe this subset as the delta in this formula here. It is bound by certain equations, where the first two equations just say it has to be a probability distribution, and the third one says you have to satisfy epsilon LDP. Well, for now, what these equations are precisely doesn't really matter. What matters to us is that these equations are all linear, and that means that this delta that we get is a polyhedron. It's a polyhedron of dimension a squared minus a, in fact. And what we want to do is we want to maximize mutual information over this polyhedron. You can express mutual information as a function in G, which is what I have done on this line. The precise formulation doesn't matter too much. What matters is that this function f is convex in G. And since delta is a polyhedron, that means that the maximum of f over delta is obtained in a vertex of delta. And we want to find the maximum to find the optimal LDP protocol. So basically what we have found is that if we can find the vertices of this polyhedron delta, then we can find the optimal epsilon LDP protocol, namely by just looking at all vertices, calculating the value of f in them, and then taking the maximum. Well, vertex enumeration is a problem from computer science. It's a bit difficult problem, But it is something we can solve, at least for small dimensions. So that means that we can find the optimal epsilon LDP protocol. Now let us look at LIP. Um, this is a bit of a similar theme, but we're going to do it slightly differently. So before we said that Q can be given by the matrix G of probabilities of Y given X. But there's another way to give Q, and that is to look at the matrix of probabilities of X given Y, so input given output, together with the vector theta of output probabilities. Well, these should satisfy that J times theta is the probability vector of X. But if you have such a J and theta, then you can work out what your protocol Q is going to be. And if you formulate it in this way, then we can characterize the epsilon LIP condition by the following, namely that every column of this matrix, JY, should be in a polygon called gamma. And gamma is again given by three equations, where the first two say that it has to be a probability distribution, and the third one characterizes the LIP condition. But basically it works the same. So Q is an epsilon LIP protocol if and only if all the columns of J are in this gamma. And from that we get a theorem, which I'm not really going to explain now, that if you want the optimal Q, then in fact this JY doesn't only have to be an element of gamma, but it has to be a vertex of gamma. And then if we know the vertices of gamma, then we can find theta and J via a linear optimization problem. Well, linear optimization is something that's relatively easy to solve. So then it comes down to the following. Again, something similar to what we have found with LDP, that if we know the vertices of gamma, then we can find the optimal LIP protocol. So we can optimize both LDP and LIP, but there is some difference in it. Namely, if you look at vertex enumeration is a problem that can be solved, but it's hard computationally, and it becomes harder the larger your dimensions are, the larger the dimension of your polygon is. Well, if we then look at LDP and LIP, the polyhedron in LDP has dimension a squared minus a. This is the polyhedron delta that we discussed. While the polyhedron gamma has dimension a minus 1. And since the vertex enumeration is by far the most difficult step in finding the optimal protocols, that means that LIP will be significantly faster. In fact, in some of my experiments, what I found that even if you take very low values, for example, C is 2 and A is 5, you get a difference in time of about 5,000, which is huge. But the disadvantage is that even though LIP is faster, both methods will become computationally infeasible for large A, because then the dimension just blows up, and with the dimension, the time complexity. So what have we learned today? We have solved the problem of finding a way to sanitize a data set that maximizes utility given the privacy requirement of epsilon LDP or epsilon LIP. Both of these are stronger privacy guarantees than the original privacy funnel, and they give privacy guarantees to all users in the database and not just the average user. Within these privacy constraints, we can find optimal utility, and we have found that LIP is a more sensible privacy metric than LDP, and is also faster to optimize. So I would advise everyone to use LIP as a privacy metric in this scenario. And finally, a bit negative result is that we can do this optimization, but only if the input space is relatively small, because otherwise the vertex enumeration will just become too difficult. And that's why in my current work, I am trying to find explicit protocols Q that give at least a decent utility, if not optimal, but that can be found a lot faster. Thank you very much.